Because more than just one molecule of initiator is required to get radical chain reactions to go to completion, it's clear that something else must be going on within propagation to prevent it from being 100% efficient. And the culprit here is termination, the coupling of radical intermediates within propagation which halts or terminates the chain. In this video, we'll learn what termination reactions are, how to draw systematically the products of termination reactions in a radical chain mechanism, and we'll summarize radical hydrobromination of an alkene, looking at the initiation, propagation, and termination steps from a bird's eye view. To begin thinking about termination, I actually wanted to start with the steps of propagation that we listed in the last video. I've taken out the input bromine radical from initiation, and from the cyclic nature of this mechanism, it becomes apparent that we really kind of only need one bromine atom to be present at any given time in order to convert all substrate to product, since more bromine atoms are generated as HBr reacts. This isn't true in practice. In a sense, it's a good thing, right? Because if only one radical was all that was necessary to convert all of the substrate into product, it'd be very difficult to control this reaction. We need more than just one molecule of initiator and more than one bromine atom around in the reaction mixture to convert all of the substrate to product. What this suggests is that these radical intermediates are being siphoned off of propagation through side reactions. And in general, the problem here is radical-radical coupling, which is an extremely favorable elementary step, since it converts a radical into an even electron species. And so the general problem here is that radical species that are floating around in the reaction mixture, let's call them R prime dot, R prime to distinguish these radicals from this R fragment within the substrate, and these will couple very rapidly as soon as they collide with these other radical intermediates to give stable, even electron products. And the key here is that the formation of these products does not regenerate Br dot. On the contrary, as this step on the left shows very clearly, these steps consume Br dot, which requires the intervention of more initiator to generate bromine radical to compensate for these side reactions. These side reactions are what we refer to as termination, the coupling of two radical intermediates that terminates the radical chain. Let's get a little more concrete now. What exactly do we mean by these R prime radicals? Well, these radicals are simply the radical intermediates of propagation. So to systematically draw the termination steps and termination products associated with the particular radical chain mechanism, we need only consider the radical intermediates involved in propagation. And here there are two, the bromine radical and this alkyl radical. By systematically considering all the ways that these radical intermediates can couple with each other, we can easily draw all of the expected products of termination. Let's do that now. So on the right-hand side here, I'm going to write all of the radical intermediates involved in propagation, the bromine radical and this alkyl halide radical. Let's call them A and B, just so we can shorten up their names a little bit. And there are three ways, actually, that we can combine these radical intermediates with themselves or with each other. We can combine A with itself, A plus A. We can combine B with itself, B plus B. And we can combine A and B with each other. When two bromine radicals couple, the product that we end up with is simply elemental bromine, Br2. And so a fun thing to note about this is that if the reaction mixture turns yellowish-brown, that's due to the formation of Br2 within the reaction mixture as a consequence of termination. When two alkyl radicals combine, we end up with a product that contains a large number of carbons, and a new carbon-carbon bond formed through coupling of the two alkyl radicals. It may look interesting due to the formation of a new carbon-carbon bond, but it's not what we want out of this reaction because it terminates the radical chain. When an alkyl radical combines with a bromine radical, we end up with a vicinal dihalide, a product of the addition of Br2, apparently anyway, across the two atoms of the alkene. And here again, as interesting as this product may appear, it's not what we want out of this reaction. What we want is hydrobromination. And this coupling event terminates the radical chain. In fact, we've got a better way to do this, right? Just by treating the alkene with Br2. And at this point, we're done. We've generated all the possible products of termination by systematically coupling the radical intermediates from propagation. When you have more than two intermediates, the possibilities grow fairly rapidly as we consider pairwise combinations of three or more radical intermediates. Even so, we can approach the problem systematically by listing out the radical intermediates and coupling them pairwise. It might be a long-winded problem to solve, but it's an easy problem to solve. Let's finish with an overview of the radical chain mechanism of hydrobromination mediated by hydrogen peroxide or some other radical initiator. In the initiation stage, the initiator's weak bond breaks homolytically, forming radicals. One of these radicals engages with one of the substrates to generate the propagating radical, which here is Br dot. Br dot then moves to the propagation stage, where it engages with the other substrate molecule to generate a radical intermediate. In the second and last step of this propagation stage, the other substrate becomes involved, and a new bromine radical is generated from HBr. Of course, this bromine radical then goes on to collide with another molecule of substrate, carrying forward the chain of propagation. These two radical intermediates in the propagation stage, A and B, as we labeled them previously, can couple with each other to form termination products, A plus A plus B, and B plus B. Now that we have the entire mechanism laid down here, we can see a really interesting balance between propagation and termination coming in. Looking only at propagation, if we want the reaction to go quickly and efficiently, it seems like we want there to be a high concentration of radical intermediates in the reaction mixture. That makes these propagation steps relatively rapid. However, that also makes termination rapid, since those same radical intermediates are involved in termination events as well. This means that we really want to make the concentration of radicals high enough that the reaction proceeds at an appreciable rate within the propagation phase, but not so high that termination starts to dominate. And so we often play with the amount of initiator used to achieve that right balance between propagation and termination rates.